Good afternoon. This is Richard Haas, and we're going to be discussing this week out of our combustion and fire chemistry book. We're going to be talking about uh, the actual chemistry portion of fire chemistry. So, hopefully, everyone has their book by now, and we're ready to rock and roll. And as promised, we're going to try to do two different assignments every week. There'll be a discussion question or an assignment, and then there'll also be our chapter quiz and our chapter. So you're responsible for reading the chapter, responsible for listening to this lecture and going through the PowerPoint. You're welcome to use any of the other features that are on the Jones and Bartlett site. And then you're going to go through and take your chapter quiz on the Jones and Bartlett, and then you're going to come back to your Canvas, and you're going to go ahead and you're going to do your discussion question. This week we have a case study of an anhydrous ammonia leak that happened in Louisiana. And I want you guys to go deeper than just the questions that I asked. I want you to think about what could actually have been done to prevent the incident, more than just leak detection and alarms and that type of thing, which are all good. But as a response mode, do some research on the internet and do a nice college level paper. Remember, we don't just go into the text box on Canvas and just start free typing. You need to put a title and center it, or justify it all the way left. Put the date, put your name. So I want you guys to do college level work. This is going to pay dividends later in your fire service career. All right, so let's go ahead and get started, and we'll start going through. Our learning objectives for this week are understand and explain the basic structure of atoms, explain how atomic structure determines the behavior of elements and compounds, understand basic chemical and physical properties and concepts and how they influence the behavior of materials involved in fires and hazardous material incidents. We're going to correlate chemical structure with chemical names to predict some hazardous chemical behaviors. For example, the metals, as an IUM, the metals, titanium, aluminum, magnesium, all in the fine shavings. If they're, for example, they go through a milling process and a machining process, they make shavings. Those things are extremely flammable and they burn very hot. We're going to understand key physical properties of chemicals and how these relate to fire. So the Dixie Cold Storage Plant, that happened in 1984. There is actually quite a bit of information available on the internet. So do a bit of research and then come up with a nice, clean, crisp paper that you're going to turn in. And then if you want to use a text box, that's fine. So with Canvas, you can actually go ahead and type it in Word. And then you can just go in and upload it into that text box if you choose to do that. Or you can type it directly into the text box. If you're typing in the text box, like we said before, do a nice clean job, right? So anhydrous ammonia leak at Dixie Cold Storage ended up with the hazmat team going in, and they had ammonia that was in between its LEL and its UEL, and it reached an ignition source. It ignited and resulted in a fatal explosion with obviously a great amount of fire. So these are things that we need to know as firefighters and hazardous material technicians. So take a deep dive on that and figure out what could be done. And then here's some of the questions that they actually asked for you to answer in the book in your case study. I've attached some other questions as well. So go ahead and take a look at that. And then that's, I believe you have until next week, the 20th, I believe, to turn that in. And then we're going to be operating on a week-by-week basis now. Today's Sunday. I ended up having to work overtime yesterday, so I was unable to get this posted yesterday, but it's going to be up. Your quiz will be turned on tonight, and then you guys are going to be able to go ahead and start working on your week's worth of work. It'll all be due Saturday. All of your work will be due at Saturday at midnight. So that's your Jones and Bartlett quiz and your case study for the week. And then I will actually put another case study up next week And then so every week you'll have your chapter reading, you'll have your case study, and then we'll work together to get through all of this. And then obviously have a break at Thanksgiving, and then back at it, and then last day of class somewhere around the 19th of December. So atoms. So for those of you that are intimidated by fire chemistry and physics and the name, we are not going to do a full fire chemistry class and a full fire physics class. This is an overview to give you guys the idea of what happens during the combustion process so you can just be better firefighters. So just so you guys know, I worked 4 days in a row. So if you hear me take a pause, I'm actually drinking a Reign energy drink right now. This is a commercial for Reign Total Body Fuel with 300 milligrams of natural caffeine. So as you guys hear me taking a pause, I'm just taking a swig off my element or my Reign. So basically, the basic building block of everything that we see, everything that we touch, everything that we can taste and feel is all made up of atoms, which is the smallest part that make up our elements. And then the elements that we have can combine to form molecules. Molecules are atoms that are bound together by different types of strong bonds. So here's a picture of it's the standard atomic structure that you'll see in pretty much every textbook. So we have protons, neutrons, and electrons. So neutron in the middle next to the proton, and remember pro for positive. And then I used to get this backwards when I was taking my chemistry classes back in like 8th grade, is I always wanted to I thought neutrons were neutral, but the electron in the valence around the outside is actually the negative charge particle. And then the proton in the center is actually the positive charge. All of the ones that are grouped together in the middle of the atom are called the nucleus, right? And the nucleus meaning the center of. So atoms are going to bond together to make different things. So for example, we have sodium and chloride, right? So sodium chloride, and if you guys know, I'm sure you've heard of this before, but this is table salt, right? So your valence electrons are running around the outside and they're constantly moving on both the sodium and on the chloride atom, and they're spinning in whatever direction. Appears that they have a way this one's illustrated, this one's spinning in the clockwise direction, but they're spinning in different directions at different times. One of the things that creates a stable ion is called the octet rule. The octet rule means that there's 2, 4, 6, 8 electrons in the outer valence. So this is the valences. This happens to have a total of 1, 2, 3 valences. And then you have your negative and positive ions, and they have a negative ion is called an anion, which means basically without charge, and a cation is positive and has a positive electrical charge. And then the basic chemical bonds that we see out there are ionic and covalent, and we're going to talk about that here in just a little bit more in just a second. And you can see when they combine together, so we have that positive and that negative, and they're sharing that electron, so that way they bond together. They want to stick together, okay? So you've got different types of bonds. You have single, double, triple, and resonant bonds. So hydrogen, that's the number one in the periodic table of elements, right? It's the lightest molecule that we have, right? So 2 atoms of hydrogen combine together to create H2, and that is the molecule of hydrogen. Hydrogen is very flammable, and it's also the lightest gas. So if you remember back to your history when they had the Hindenburg that actually was crashed, I believe, on landing, and it burst into flames and burned very rapidly because of the hydrogen gas that was keeping the blimp afloat. You have a double bond. So carbon dioxide has basically two molecules of oxygen and then one molecule of carbon, and they're bonded on either side. Okay. And then you'll notice it's 1, 2, 1, 2, 1, 2, and 1, 2. Hydrogen is 1, 1, and then a triple bond. So don't take that because there's three together that makes that a triple bond. It's the number of valence electrons that are actually sharing and binding together that cause it to be a single, double, or triple bonded atom. Okay, atoms creating molecules. So this is nitrogen. Nitrogen makes up 70% of 78% of the air that we breathe in. So right now you're breathing in 21% oxygen, 78% of nitrogen gas, and then so that totals to 99. And then we have 1% of what we call trace gases in the air that we breathe, and there are things like neon gas. There is obviously we have carbon dioxide in the air. We have all different types of argon. There's a whole list of gases that fit into that 1% of the air that we breathe in. Okay, elements. Elements are the simplest form of matter. And then later on, we're going to talk about halogenated compounds, and then we're going to talk about atomic numbers, and we're going to talk about the atomic weight. So for those of you guys back in late middle school or early high school, you're going to remember this one, the periodic table of elements. Here's our hydrogen right here, the lightest gas. And then it goes all the way down to the bottom here with our heaviest gas. And these are going to be grouped together by periods, groups, and families. And they utilize the colors for those so that they all are joined together so that they basically are able to, we are able to take a look at them. And here's your gases over here. So we have helium, neon, argon, xenon, radon, which is a radioactive gas, and it's in our air that we have right now. And Kr, and I can't remember that one right off the top of my head right now. See if we can zoom in on that. And I have old eyes, so, and that's krypton gas, okay? So those are those trace gases that we talked about. And then we also have, remember we talked about our carbon in the air. Well, I'm sorry, that could be a solid as well, but our nitrogen in the air and our oxygen in the air. And then we'll discuss how we can take a solid and we can turn it into a gas by heating it. Okay, so those are our periodic table of elements. Molecules are bound by chemical bonds. This is basically just a piece of wood. And so wood can actually is a solid, obviously, and then but it can be converted into a gas. When people see wood burning, they think it's actually the wood that's burning. It's not. It's the wood is being heated by whatever flame or ignition source, whether it's lightning in the middle of the forest or somebody takes a Bic lighter and lights a campfire and applies heat to wood and it begins to off gas. That's process is called pyrolysis. So in pyrolysis, the wood is heated, it releases a gas, and the gas starts to burn. So wood typically cannot be created into a liquid without being changed by using something like a strong acid, and where you are going to dissolve the cellulose material, which is what they do in paper pulp manufacturing processes when they make paper. They do that. So think of this as individual molecules, and then they're held together by their chemical bonding like we saw before, and then all the wood is going to have individual cells. And you'll see the grain on the outside of the wood, and it'll be solid. You can pick it up. It smells good. It smells like pine or hickory or whatever wood that the tree species that it came from. But it all starts out, you have the molecules, and then you have the compounds, and then it goes all the way down to the cell wall for the smallest portion of it. So they're always in constant motion. This is greatly illustrated in metal, where we take a piece of steel and we heat it with an oxygen acetylene torch and we get it red hot, and we can literally move it around. And the molecules are so active in metal that you can literally heat one end of a 1 foot long metal bar and hold the other one with your bare hand, and it won't be long before you're not going to be able to hold on to it anymore, because the heat is actually, number one, the metal is an excellent conductor of heat, but the molecules are getting excited and moving around, and the friction of the molecules basically banging into each other is transferring that heat all the way down to the other end, which would have been cold earlier on. All right, so, and then we're going to talk about chemical changing versus physical changes in molecules as well later on. So compounds, physical properties of compounds must be a fixed ratio. For example, we have the chemical formula of H2O. Everybody knows that as water, right? So if we have, so it's 2 hydrogen molecules and 1 oxygen molecule bound together through our covalent bonding or ionic bonding, and then it creates a compound, which is 2 or more things from the periodic table of elements formed together to make something else, right? So that is how water is actually, you could separate that, and there's been people that have been trying to break that covalent bond and separate the hydrogen off of the oxygen. So now think if we went H2 and we only have 1 oxygen molecule, if it was H2O2, then we would actually have a different compound than water. It would be something completely different. So depending on how they bond and how many molecule numbers on each different of the element from the periodic table of elements is going to change what the compound comes out to be. So decomposition temperature is basically when something begins to decompose on its own. For example, if anybody's ever mowed their grass and they've dumped that green grass clippings into the yard hopper, the green yard hopper for the garbage man or garbage person to come by and pick that up, and you go out there a couple days later in the summertime and you open it up and you can just feel the heat coming off of that, right? So you're actually having decomposition taking place of that grass, and the chemicals, they're breaking down, right? So you have chlorophyll. Plants and animals, including us, are carbon-based. We're made out of carbon, right? And then if we were to allow that in the right circumstances to continue to decompose, it would actually begin to combust. This happens when you bale hay, and let's say they cut all the hay and then it rains, and they don't let it dry out all the way before they bale it up, and there's moisture baled in with the hay begins to decompose, and then you get a process called spontaneous combustion, because the decomposition of the material creates a large amount of heat, enough for it to actually catch on fire. So mixtures are different than compounds, and those are substances that are held together by physical means, not chemical bonds. So think of, for example, concrete, right? So concrete, we're going to take rock, sand, water, and then we're going to take cement powder, which is actually baked and pulverized limestone. So they take regular limestone, they harvest it out of the mountainside, they bake it at a high temperature, they turn it into a powder, and that's called Portland cement. And it was actually discovered in Portland, not Oregon, but in Portland, England, and it radically transformed how we build buildings. So we mix sand and cement and water, it makes what's called brick mortar. Or we add sand, cement, and rocks of different sizes and ratios to create concrete. But that's a mixture, right? We do have a chemical chain reaction that happens when the water and the pulverized limestone comes together, and we'll talk about that more as an exothermic reaction later on in this lecture. And then, but think about the examples that are out there. So you have soil, rock, and air. So air is a mixture of oxygen, and then we have our nitrogen, and we have our xenon gas, and our helium, and our neon gases, and all those things. They're not binding together, right? They're all mixed throughout the air that we breathe, that you literally are breathing right now, but they're not chemically bonding together and making new compounds, because that would end up being incompatible with life, right? So here's kind of an unusual thing to note is that, so ambient air that we breathe is 20.99 to 21.00% oxygen. So fire needs oxygen to breathe. Mammals and fish and reptiles all need oxygen to live. And it's an oxidizing process that happens in our blood. When you guys go through paramedic school, you're going to learn all about Fe2, which is basically the iron in your blood, which gives it its color. And basically, so your blood is rusty because we breathe in oxygen, gets carried to the cells by our red blood cell, RBC. And then the RBC actually, the oxygen attaches to it, and then it gets dropped off at an individual cell to oxygenate it. And then that same RBC will pick up waste products, as in carbon dioxide, and then as you exhale it, you'll blow off carbon dioxide. So we breathe in 21% air, and we exhale out 15%. We inhale 21% oxygen in our ambient air, and we breathe out 15% of our breath is oxygen. And so fire burns very well at 21%, but as we get down to the 15% mark, fire begins to not burn very well and actually starts to smolder. So you'll see a direct correlation to how the human body works and how fire works, and how fire burns. All right, so ingredients of the mixture retain their own properties. So oxygen is still oxygen, argon is still argon, nitrogen is still nitrogen. Okay. So talking about unique names, in the Department of Transportation 49 Code of Federal Regulations, Section 172-101, we learn about our prefixes for our chemical names. You're going to go over this in great detail when you take your hazardous material class. So we have prefixes and suffixes that are going to give us a really good idea of talking about different materials and what they are. So INE, chlorine, right? The suffix INE is chlorine by itself. Sodium chloride, IDE, is a chlorine and sodium mixed together, which is sodium chloride, which is a molecule that we looked at in the first couple slides. That's salt. Sodium chlorite, you'll notice that it's got an oxygen molecule attached to it, so it's NaCl and then NaClO2. So it's chlorine with sodium and two oxygen molecules on it, turns it into an ITE. Sodium chlorate is sodium chloride and then O3. So that's got that 3 oxygen component on it, which is ATE. And then you have ammonium perchlorate, which is now that is nitrogen. Ammonia is basically when ammonia is mixed into water, it actually turns into nitrogen, which is fertilizer, liquid fertilizer. Ammonia and perchloric acid, 4 atoms of hydrogen and 4 atoms of oxygen, and this is a powerful explosive. So you can take something as simple as chlorine, and you can work your way down the chain, and then you end up with ammonium perchlorate, still a nitrogen-based dealio. This is a sodium base, and NH4 is nitrogen. I said this was nitrogen. That was wrong. This is sodium base. So the sodium is the first. This is sodium, and this is nitrogen. Organic chemicals contain hydrocarbons, carbon forming strong bonds. You have organic peroxide, which can be very explosive, oxidizing agents, and then redox reactions, and they can be very violent chemical chain reactions. So Oxidizing agents. Number one, oxygen, right? So if we take a candle and we light it, we take a glass mason jar, flip it upside down, and then we place it over the candle, so we're basically covering it like a lens. It's going to burn for a little while until we start reducing the oxygen down below that 15%, and then the candle's going to go out. So fire needs an oxidizing agent to sustain. There's other oxidizing agents out there other than oxygen that we have in the chemical world that we use for all different types of processes, but they're all considered oxidizing agents. So because all atoms of a certain element have the same structure, they also have the same properties, right? So that means that they're going to decompose at the same temperature. They're going to react violently at the same temperature. So they're going to have the same basic properties of each other. And we're going to talk a little bit about temperature scales. So we use Fahrenheit typically in the United States for all of our weather. Over in the rest of the world, they use Celsius or centigrade. You'll notice in a lot of science, they're going to use centigrade, and then in the medical field, we use centigrade, and we also use the metric system for all of our medication administrations. So we say we're going to give the patient 1 liter of fluid, we're going to give them 10 cc's of a medication. So that has been adopted a long time ago. So here's some of the temperatures and the boiling points. So think about this in a boiling point. A lot of products actually out there will boil at very, very cold temperatures. So carbon dioxide, which is how we make dry ice, right? It has a boiling point of 109 degrees below 0 Fahrenheit. Benzene, which is used in the manufacturing of diesel fuel and solvents and paint thinners and stuff, it has a boiling point of 176.18 degrees. So that's just not going to boil when you open up the lid. This carbon dioxide is going to immediately turn to gas when it's exposed to ambient air, unless it's at 109 degrees below 0, and then it'll stay a liquid. Okay? Chlorine, in its gaseous state, we can take chlorine and we can refrigerate it or pressurize it and turn it into a liquid, and it will literally be a liquid at minus 29 degrees Fahrenheit. So in Alaska, in the wintertime, if you had a cask or a 1-ton cask of chlorine, which is what it's carried on most of the time for chlorinating pools and the water that we drink to get rid of bacteria, that chlorine, you can open it up at 40 below 0 in a liquid and it would not off-gas at all. You could spill it and it would leak onto the ground, but it would have to get above negative 29 degrees for it to turn back into a gas. Hydrogen gas. Hydrogen can actually be made into a liquid too, but it's got to be cooled to minus 423 degrees. Oxygen. We have a lot of liquid oxygen around our communities. You'll see they call it LOX or LOX for liquid oxygen. OX is the abbreviation for oxygen, and LOX is found at hospitals and medical clinics and dentist's office for giving patients oxygen during their procedures. And so you think the reason why they liquefy it is so that they can have more of it and you don't have to continuously replace the pressurized cylinders of just the pure 100% oxygen gas. So they refrigerate it, called a cryogenic liquid, and then they put it into these specialized, called a Dewar. And a Dewar is a container, it's basically like a giant thermos bottle. And we keep that liquid in there cold, and when they need it, they open up, crack the valve open, and the top portion of that Dewar is above 297, so the liquid is becoming a gas, and then it escapes out the tubing that it's supposed to escape out of, and then it goes to wherever it needs to go throughout the hospital or the clinic or whatever, so you can supply oxygen to your patients. So you also see here that you have water, and so water it's going to boil at 212 degrees Fahrenheit or 100 degrees Celsius, and water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Okay, vapor pressure, flash point, open and closed cup, fire point, and vapor density. So vapor pressure basically is the vapor, is the pressure that comes off of it, and that's determined by that negative number that we were just talking about. And each individual material can turn into a vapor depending on the temperature that's put onto it. For example, we can take lead, so Pb on the periodic table of elements, and we can heat that enough that it's going to turn into a liquid, and we continue to heat it until it turns into a gas and actually reaches its vapor pressure temperature, and then it's going to release into the atmosphere, right? Now, for materials that are actually flammable, so for example, if we take cooking oil on the stove and we pour it into, and this is how the open cup test works. We put it in a pan and we turn it on, okay? We turn it on low, and we take an aim and flame barbecue lighter and we click it above the oil. Nothing happens, okay? We're not at its vapor pressure yet. We're not at its flash point. And the flash point is simply described as the temperature of the material to where it makes enough vapor to flash into a fire and then automatically go back out without staying burning. The fire point is when the material reaches its temperature to where it's giving off enough vapor that it actually will light on fire and stay on fire. So flash point, basically you get a whoosh of fire, it goes right back out again. As we continue to warm up that cooking oil, and then we go into and we click the aim and flame lighter, and then it catches on fire and stays on fire, that is our fire point. And the open cup test is a scientific test to determine the flash point and fire point of any given liquid material that's either flammable or combustible. So you know that flammable materials, when we say flammable, that doesn't mean everything, right? So anything that has a flash point and fire point below 100 degrees Fahrenheit is considered flammable. Anything that is going to flash or is going to catch fire and stay on fire above 100 degrees Fahrenheit is called combustible. So that's something you need to file away in your memory bank, that the difference between flammable and combustible is that 100 degree Fahrenheit line, right? Closed cup test is very similar to what we talked about. We put the material in the pan, but it's all sealed up, right? So it's closed in a closed cup versus an open cup. But you can do this if we had a lab that we could actually work in and we weren't doing this online. We'd have a Bunsen burner. I'd put some olive oil in there or some canola oil, and we heat it up, and then we'd use an aim and flame lighter. We'd have somebody holding a thermometer in there, and then we would know at what temperature the flash point was when we click the lighter, and then we check it every couple degrees as it goes up in temperature. It flashes. We know the flash point, and then we keep doing it, and then when we light it again and it flashes and stays lit, that's our fire point, okay? Vapor density is the density of the vapor or the gas as it is compared to air, which is 1. And it'll come up in the next couple of slides. We'll talk about it more. Solubility. Solubility is the ability to mix chemicals together. And doesn't mean, right, we're talking mixture, like we said before, dirt, where we have leaves and sand and different organic matter that you could separate them out under a microscope and tell them apart, versus an element, right? Or a molecule, which are individual. So remember, molecules are made up of atoms, and then the molecules make up the elements, which are many molecules together, and then we can mix that. So solubility is a maximum amount of substance that can be dissolved in another substance. So think about this. So you're making pancakes, and it says put in 1 cup of water, and you're going to put in 3 cups of the Krusty's pancake mix, and you mix it up, and it's a good pancake consistency, right? You keep putting more and more powder into that mixture. It's going to get to the point where you cannot dissolve any more powder. There's going to be lumps of dry Krusty's pancake mix in there, and it's going to get thicker and thicker, and you're not going to be able to mix it anymore. So that's solubility. Solubility is the maximum amount of material that can be mixed in a given thing, whether it's water, whether it's a petroleum-based solvent or whatever it is, okay? And then we're going to talk about polar solvents and non-polar solvents. Your polar solvents right now that are very popular in California, we use a product called ethyl alcohol in our gasoline. We run about 10%. They change the mixture a little bit. They call it summer and winter blend. Alcohol burns very clean. It has no flame. It creates no smoke. So this is ETOH, the same alcohol that's in wine, beer, liquor. It's the same alcohol, but they make it out of corn. And they literally in Iowa, and they make rail cars full of this stuff, and they mix it with our gasoline to make it burn cleaner, so we create less smog. So polar solvents are your lacquer thinners, enamel reducers, your alcohols, and then non-polar solvents are things like mineral spirits, naphtha, which is a byproduct of making gasoline. Those are all solvents they use in painting, the painting industry. And then there's a whole array of different chemicals they use in automotive painting that fall into polar and non-polar solvents that are out there. Okay, talking about water, and we said that air, and then I'm going to go ahead and cover this now, just so we don't miss it, is when we talk about air, is vapor density, is as to water is 1. We use water as a measurement, and we use air as a measurement of 1. Water, obviously, is the liquid that we use to measure other liquids against. So, for example, mercury. Mercury is a very heavy liquid metal, and it will automatically drop to the bottom of water. Gasoline is also a liquid, and it is very light, and it will actually, because of its molecular makeup, it will float on the surface of water. So water is specific gravity, and vapor density is what so we have water, specific gravity, vapor density is air. Air is equal to 1. Propane is heavy. It weighs 1.5 is what they say, and that it will actually sink in the air. That's why when we have a propane leak, it's quite dangerous because it settles in the low areas, goes into storm drains, and all it needs is an ignition source, and it'll burn and explode. Natural gas, which is what we typically heat our houses with unless you live in the country, is 0.55. So it's about half of the weight of air, which is 1, and it will literally be able to ventilate off and it'll dissipate out into the atmosphere. So natural gas leaks in a home, if it's an outside leak, are very seldom do they cause problems. The problem is when they leak inside of a building, and then they accumulate, find an ignition source, and that's the one where you guys have seen on the news where all the walls of the house are all laying in the street, and the house is completely blown into toothpicks. So that's your natural gas that is accumulating inside there. So the little illustration here called boil over, they used to make our petroleum storage tanks without lids. So you would have crude oil there, and on the top of that, there was no lid at all. So they would fill it up and they would drain it and fill it up and drain it as the crude oil was harvested out of the ground or brought in by ship or whatever. They were pipeline and filling them up and at the refineries, and then they make it into gasoline, they make it into diesel fuel, jet fuel, all the things that we need for transportation. And then they found that if you dump straight water in there to put the fire out, it's going to cool it, but putting water on a grease fire is never a really great idea. So what happens is the waters begin to boil, and remember that the oil is lighter, even though it's thick, it's lighter than the water. It's going to float on top. So the water then begins to sink, it boils, and then it'll literally boil over the top of the vessel, and then next thing you know, you have fire everywhere all over the ground. So now they've created, and this has been decades since they came up with the idea, but they have what's called a floating lid. It's a big metal lid that sits on top of the crude oil, and it literally just rests there. So the crude oil keeps it from sinking. There's a rubber gasket all the way around the outside. As they fill it, the lid lifts up, and then as they drain it, the lid slides down. It basically just slides up and down inside that vessel, and then creating basically a seal over the top so that it can't catch on fire, or helps if it does catch on fire. So we're going to talk about auto ignition temperature, UEL, and LEL. So we're going to go back to the pan of cooking oil. So auto ignition is when you take that pan of cooking oil, and this happens every day in America where somebody turns on the stove on high. They're going to make some French fries. They put cooking oil in a pan, and then the phone rings. And they start talking to their friends, or they're scrolling on TikTok or whatever. Well, the oil is going to get hot enough that it's going to ignite without an outside ignition source. So no lighter, no candle, no nothing. You're going to begin to heat that thing up, and it's going to get so hot that it's going to get to its auto ignition temperature, and it's going to catch on fire. So all different liquid fuels, whether it's an oil or it's a gasoline or diesel fuel, all have an auto ignition temperature. Then we have what's called our UEL and our LEL. So this is what we use now. It used to be the upper flammability limit and the lower flammability limit, but they changed it to explosive. So think about gasoline. If I take gasoline, pure gasoline, and I have it with no oxygen in there whatsoever, and I light a match, it will not burn. Because you need an air-fuel mixture. We need the oxidizer mixing with the fuel. Whether it's a liquid fuel being used in an engine, whether it's a gas fuel like natural gas, you have to mix an oxidizer with the fuel at a specific ratio. And then you guys are answering your quest. The anhydrous ammonia, it has an upper and lower flammability or an upper and lower explosive limit range. So what that means is you can have too much gas, so a huge amount of propane in an area, and not enough oxygen, it won't burn. You could have way too much oxygen and not enough propane that it's below the lower explosive limit, and it won't burn. So it's got to be in that window. The gas that has the widest window is acetylene gas, which is used in the welding and fabrication industry for working with everything with steel. And it has a huge upper and lower, it has a huge window of flammability. So it's upper explosive, its UEL is very high, and its LEL is very low. Okay? All right, talking about bases and acids and our pH, right? So the body is 7.35 to 7.45. That's our perfect range of our acidity of our body. And then you can look at, like on this graph down here, so this line graph shows that below 2 is considered to be a strong acid, and lemon juice, believe it or not, is an acid, right? Vinegar. For all you soda drinkers out there, that one's real nice there. That's 3.5. So that's on very acidic, right? And then orange juice, coffee, rainwater is actually a little bit on the acidic side because they're saying because of the pollution in the air and from us burning petrochemicals that it causes that. But we didn't have the ability to test rainwater before we were driving cars, so we don't know that for a fact. That acidity could simply be from just carbon particles in the air, for example, from volcanic eruptions and giant forest fires that used to go on thousands of years before we were here when it was just the Native Americans that were occupying the United States. So we don't know that. So the right in dead smack in the middle is 7, which is considered neutral. This is 14 is considered very alkalinic. And 0 is the lowest, and that's the highest, strongest acid you can have is 0. And then shampoo is a little bit alkalinic. Seawater is alkalinic. Baking soda is actually an alkali, so it's alkalinic. Soap water, milk of magnesia that you take for constipation is alkalinic. Ammonia water, and then lime water. All of these are very strong bases. So base is alkaline, and acidic, and acid is acidic. Okay. Matter. Chemical properties of matter. We have basically inorganic and organic matter. And then we have basically 3 different states of matter: solid, liquids, and gases. So, for example, wood, solid, right? We can convert that into a gas by heating it through the process called pyrolysis. Water, interestingly enough, at absolute Kelvin, which is a extremely low temperature, below like 450 degrees, water can actually exist in all three states of matter at the same time. So it can be a solid, it can be vapor, and it can also be droplets of liquid at that extremely low temperature. So it's a phenomenon that has been recorded, but they don't exactly know why. And that's at standard pressure, which means standard pressure is regular atmospheric pressure, which is 14.7 psi. That's the pressure in the air that we are breathing right now. There's pressure, there's gravitational down pull on us. Obviously, it keeps us from floating around. And then we have atmospheric pressure. And that pressure, basically, when you go to take a breath, you're not actually actively breathing in. You're opening your mouth and allowing your lungs to open up. And then 14.7 pounds of pressure of that air flows into your lungs. Exhaling is actually the physical portion of breathing. So where you actually use your muscles, accessory muscles, intercostal muscles around your ribs, and then that forces the air out of your lungs, okay? So remember, flammable gases can be stored as a liquid. Flammable gases cannot be transformed into a solid, but they can definitely be put into a liquid. Some solids can become liquids and gases, but for example, wood, unless we add an acid to it, but in its natural state, just using fire, we can't take wood as a solid and turn it into a liquid, into a gas. It goes from a solid, we apply heat to it, it goes through a chemical process called pyrolysis, and then it becomes a gas, and then it burns if you catch it on fire. So we got Boyle's law, and then we've got Charles' law. So Boyle's law is that you can basically compress gas and turn it into a liquid with pressure. So that's how they move propane around. So if anybody's filled up their barbecue bottle, you go to the local gas station, they hook that machine to it, and they pump it over. Well, they're actually pumping liquid from one bottle into another. But at some point, they take that natural gas, or that propane gas, that's, by the way, a byproduct of making gasoline. So next time you pay $5 a gallon for propane, you know that they're making extra money off of that, because that's actually a byproduct of making the product gasoline and diesel fuel. So with Boyle's law, we take a gas, let's say oxygen. We have 100% pure oxygen, and we put it in a special pump, and it begins to pressurize it, and we force it into a very strong steel vessel. As the pressure increases, it's going to force the gas to basically change state of matter from a gas into a liquid, okay? Then Charles' law is where we take a gas and we cool it, and we cool the gas down and becomes what's called a cryogenic liquid. You can use a combination of both, or you can use one or the other in industry to be able to make those welding gases, that LOX that we talked about, the liquid oxygen that's used in the hospital. We can refrigerate that gas, and we can pressurize it and do a combination of very, very cold and very high pressure, and we can make a lot of liquid oxygen, and we ship it all over the world. Use it for medical purposes and for oxygen acetylene welding and for different processes that need it across the world. Cryogenics, so basically is a gas that's been transformed into a liquid by pressure or by chilling it, and then it's stored and transferred. You'll see these white and green semi-trucks going down the freeway, and it's a giant thermos bottle. You'll see a thermostat on the back. It's about 6 inches around, and it's a temperature gauge, and that's an extremely cold. That's a cryogenic liquid. And those are carrying non-flammable gas, typically nitrogen. And nitrogen is used, once again, in all different types of injury. So the cryogenic liquid, once you open up the valve and begin to release it, it's going to turn from a liquid back into a gas so it can be used, right? So it's great for transportation, it's great for storage, but if you ever had that 8th grade science teacher that takes the banana and dips it into the liquid nitrogen and then throws it on the floor and it shatters into a bunch of pieces, well, that same thing can happen to you. If you get liquid nitrogen spilled on you or you get your hand into it, it's actually going to cause significant damage. Like your fingers could break off your hand. Your hand could break off your arm. So it literally flash freezes, and we're talking hundreds of degrees below zero. Okay? All right, we're talking about cryogenics, talking about the expansion ratio. When it's turned from a gas into a liquid, when it's turned back in, it expands, right? So 1 gallon of liquid nitrogen could be equal to, say, 400 cubic feet of nitrogen gas. So that's why it's so convenient to be able to make it into a cryogenic liquid, transport it, use it on site, and then take it from a liquid and turn it back into a gas, is because of its expansion ratio. Same with your barbecue bottle. If we just filled up your barbecue bottle for your propane barbecue with just gas, you might be able to get done cooking like one set of hamburgers and you'd be out of gas. But because we're able to put it in there as a liquid and then it expands, and propane expands to around, don't quote me on this, but like 216 to 1. So for 1 ounce of propane liquid, you get 216 ounces of propane gas. So that way you can go out there and you can make barbecue for the whole, first couple months of summer or the first month of summer. So that's the benefit of having that expansion ratio. So we already talked about this, propane and natural gas. Natural gas can also be made into a liquid. Raley's grocery chain has the Blue Cloud truck, zero emission. They're taking natural gas and they're actually turning it into a liquid. So they pressurize it, they refrigerate it, and then they pump it into tanks that are on the semi-trucks. And the semi-trucks are burning that natural gas. And all it puts out is carbon dioxide and water vapor. So extremely clean burning, extremely good. The problem why it's not so widespread used is because we don't have places to fill them everywhere. PG&E has places to fill them in a couple locations. Elk Grove Unified School District has the cylinders on top of all of their school buses. They run them on natural gas. Sacramento County bus line, the transportation, they have all of their buses all run on natural gas. And those ones, they're not liquid. They're using actual gas on the buses. So they have the large, strong steel cylinders on top of the bus. Next time you see a bus, you'll see a big plastic cover. It's probably 8 feet wide across the bus and, say, 16 feet long. There's a bunch of cylinders that are bolted down up there. At night, they plug it into a machine that pressurizes the natural gas, the regular natural gas that you cook with, that runs your stove, that heats your water in your home, that same natural gas. They fill those cylinders, and then they start the bus up with the same engine. They use a gasoline engine with that specifically set up to run the natural gas. You start it up, you drive it, works great. So that's some of what we call the alternative fuels that are out there that we're seeing, and they actually work out quite well. Dust. People don't necessarily think that dust is explosive, but I can tell you that if you do any studying on taking a look at some of the grain silo incidents that we've had across the Midwest, where you're grinding, or even cabinet shops and lumber mills, where you have that super fine dust from cutting wood or any organic material, wood, straw, grains like wheat, oats, when there's a fine dust that's created, if that fine dust gets between its UEL and its LEL and has the correct amount of oxygen, it will burn amazing, right? Like it will explode. So next time you're camping and you have a campfire going, don't do this in your kitchen. Take just a tiny bit of flour or pancake batter mix, put it in between your fingers, and sprinkle it over the fire, and you'll see that dust just burn up. So we have safety systems built in now. We've killed a lot of farmers, we've killed a lot of truck drivers, and a lot of firefighters with these explosive grain dust issue that we have. And it's got to be an organic material that would normally burn, right? So if you have powdered rock, you're not going to get that to burn. Doesn't burn anyways. But anytime you have a a product that has a dust created with it that's actually from an organic material, it'll burn and explode. So now we have evacuation systems that actually will pump out fresh air in there to get it above its upper explosive limit, or they'll have duct fans that actually pump the dust out of it so it removes the fuel so that it can't ignite. And then we use what's called intrinsically safe motors in those processes, where the electric motors that are operating all of the augers and all of the machinery that move the product around don't make any sparks. So that's what intrinsically safe means. Our portable radios that we carry as firefighters, those are intrinsically safe. Your iPhone is actually built to be intrinsically safe as well, which means it doesn't create any spark when you turn it on or do any of those things. Now, I wouldn't test the limits on plugging it in an environment that's filled up with propane, that's in its UEL and LEL. But as far as our portable radios, those are specifically built so that way you don't cause explosion or fire. Okay, now we're going to talk about BLEVE, boiling liquid expanding vapor explosion. And this is, I'm going to post a video on this that does a way better job than me. They actually did an experiment in Nevada where they take a propane cylinder. And remember, BLEVE can happen with any liquid. So it's BLEVE, boiling liquid expanding vapor explosion. So you can take a campfire, once again, take a Pepsi in an aluminum can, and you set the can in the fire, and then it's going to start to heat up, and then it's going to start to boil, and then it's going to start expand, which means the material inside, because the molecules, right, we talked about earlier on, our atoms and our molecules are expanding, they're getting excited, and they're moving apart, and it begins to swell. The vessel that it's in, the aluminum can, is going to weaken, and then it's going to rip open, and it's going to blow Pepsi everywhere, right? Well, the same thing happens with propane, but it just so happens to be a very flammable gas and a very flammable liquid. So with a propane cylinder, when they fill it, when it gets to 80%, that means it's full. So there's a 20% portion on the top of the tank that has gas, and the 80% below is a liquid. So in a BLEVE, if we have a fire on a vehicle or a tank, a propane tank or any type of vessel, and it starts to heat the portion that's above the liquid line, that's going to start weakening the metal. The material's going to start to weaken, and then they have what's called a PRV, pressure relief valve, which we'll show you in that video, which lets off excessive pressure to prevent a BLEVE from happening. But the rapid heating of the vessel will actually, it'll overrun the ability for the PRV to keep up with releasing that pressure. The vessel fails, and then the cylinder or the vessel will then explode. And they've found the ends of the tanks right here on the left and the right as far as 3/4 to 1 mile away from where the explosion. Our first real BLEVE that we experienced in the United States was in Kingman, Arizona. We'll do a case study on that. That's very well publicized. That was back, I think, in the late 60s, early 70s. And we found out how to deal with BLEVEs, where you set up fire engines and you pump water onto the tank, and everybody backs away a half a mile to a mile away, and you just let the fire engine just keep the tank cool, and you wait for the PRV to vent it off, and then once the tank is cooled down and the fires are out, then they wait a couple of days. They can go in there and they can remove the fuel from those damaged vessels. But while they're actively burning, you cannot be near these things. They will unalive you very quickly. So talking about chemical reactions, we have a couple different types that we need to cover as far as what we're going to be dealing with here. We've got endothermic, exothermic, polymer, and then we have monomers. So anytime that you have heat absorbed in a reaction, it's called an endothermic, which means to take heat in. And anytime that you have a chemical chain reaction where it gives off heat, that is called an exothermic. So exiting out, and in, think of it drawing the heat in, and exo, where it's exiting the heat out. In an exothermic reaction, the covalent or ionic bond is being broken, which creates heat. And then when you have a bond that's being formed, it creates the bond being formed, it takes the heat in. In a polymer, I want you guys to think about, people doing a lot of epoxy tables out there nowadays and that kind of thing. So we have the substance that we use, the epoxy, and then we have the epoxy catalyst. So when we mix that together, we're going to get a poly reaction, right? Which means many. So we're going to have an exothermic reaction. So we take our clear and we add our glitter to it and our color, whatever we want, and we mix it up with a paint stick and we get it to with our consistency, and then we pour it out on the table. As that stuff goes and begins to cure, the reason that it gets hard is because of a chemical exothermic reaction. So it's actually, the bonds are being broken, and they are basically doing that to make the material cure. And then if you had the right filmmaking equipment, you could see like a vapor coming off of that as you're allowing that chemical to cure. And then it's creating that exothermic reaction. Anytime you add two substances together, that creates heat. So that is an exothermic reaction. Monomer means we have one. Polymer means many. Okay. All right, so we have materials out there that are reactive to water, and then we have things that are reactive to air. So there's different, for example, white phosphorus is basically, they use that in the military for making flares when it's exposed to the air and just the moisture in the air, because all air has some degree of moisture, right, called relative humidity, and it burns very, very bright and very, very white. That's why they use them for illumination flares during combat and that type of thing. Or they could also be used at night during search and rescue. And then water reactive materials. So for example, sodium. There's another metal. Sodium, when you take it, it comes in a can, and it's like cream cheese, but it's an actual metal. If you carve a piece of that off and you let it sit out without the mineral oil in it, just the moisture in the air, the relative humidity, will cause it to burn. If you take that piece of sodium and you throw it into water, it will actually explode. So it's extremely water reactive. So we have materials out there that are compounds, right? They're molecules that are combined with other types of molecules to make a substance. So sodium is actually by itself, it's an element, but they mix it and they use sodium in explosive manufacturing, that type of thing. So this is the Timothy McVeigh Oklahoma City bombing with the U-Haul truck, and they literally mixed fertilizer and fuel oil together, which they got the recipe from somewhere, and now you cannot buy ammonium nitrate fertilizer without a permit, and they need to know where all of it is going. So they bought this on the open market, and they mix it with fuel oil. Fuel oil is like diesel fuel. People in the Midwest, they heat their homes and older homes, some newer homes too, and they have fuel oils. They have a tank on the side of your house that the fuel oil company comes by and they fill it up once a month, and then it basically drips into a burner, and then it makes a fire, and then it blows a fan across the top of the coils, and then it heats your house. Well, they took this and they mixed it with ammonium nitrate fertilizer, and it made it into a bomb, right? So the ammonium nitrate is the oxidizer, or is an oxidizer, so ammonium, and basically it together, then they need heat and friction to be able to make it go off, and the resulting damage, as you guys probably learned about when you were in school, was catastrophic, right? So we have materials out there that are shock sensitive. So if you have it and it's like nitroglycerin, nitro is extremely shock sensitive. It's different than the nitroglycerin that we give to cardiac patients to take away their chest pain. But we're talking about the nitroglycerin that they originally made dynamite out of. So that stuff would be very unstable. If you ever watch an old Western and they got the little vial of nitroglycerin and the guy, they're like, they're going to drop it and it will literally, by just letting it hit the ground, it'll explode, right? We have all types of materials out that are unstable, that there's many different things that can cause them to react either in fire, explosion, or a polymer reaction. And then we already talked about the catalyst a little bit, so I saw that. I want to talk to that's when you mix two things together to be able to make a stronger material. So epoxies, automotive paint, all those things, we have a catalyst that goes in there to make it an exothermic reaction and causes the material to cure. So it doesn't dry, it becomes a new thing. It actually cures and becomes a solid coating over the top of your vehicle. We have materials out there incompatible. The easiest way to explain this is oil and water, right? So if you take olive oil, pour it in a cup of water, and take a look at it. So it's miscible, but it's not completely soluble. Soluble means that it will dissolve completely. So sugar, if you put sugar into water and you stir it up, particularly if the water's warm, it will actually become a solute. It will literally dissolve, or solute is the result of something dissolving, versus a mixture. And when something is mixable or mixable, right, is when you put the oil and water and you shake it up real good, or oil and vinegar for your salad. You could pour it on there, but if you were to put it back in the bottle, stick it on the counter, it's going to separate back out. You're going to have oil on top. You're going to have vinegar on the bottom. So we'll go way deep into this in hazmat and your firefighter 1 when you take your academy as a toxic materials that happen during firefighting. We have some significant, for example, hydrogen sulfide gas and cyanide. So when you burn a house, you're going to get actual cyanide gas. So we wear something called a self-contained breathing apparatus that allows us to be able to take fresh air in on our back and go inside the building, and we can go fight fire, and then we're breathing fresh air that we filled up in a specific machine that literally brings 100% clean air, and then we come out, we're not breathing all of those toxic chemicals and all those carcinogens. But we have multiple different chemicals that are going to come off. The majority of fires that we encounter today are literally from hydrocarbons. So when they make gasoline and diesel fuel, there's byproducts that are left over. That's where we get plastic. Everything that we see around us is made out of plastic. So I'm in our spare room right now. Carpet is made out of nylon. Nylon is a plastic. I'm looking at this little Wi-Fi. My wife's got the Wi-Fi password for our house with little plastic beads all over it. We have a chair that's got a nylon blanket, a nylon pillow, polyethylene foam, which is ethylene is a product of, it's an ethylene, which is an ethyl product, which is it was another carbon or crude oil based product. So all around us, we're having these fires that are showing up, and these house fires, and what I call the Walmart generation, because we buy everything, it's inexpensive. We got the plastic folding tables, plastic cups, plastic plates, plastic everything, right? Our carpets, our clothing, our nylon, polyester, all of those things are plastics, and they all give off extremely toxic chemicals. That is why you have to wear a breathing apparatus when you're fighting fire. All right. Go through our summary. We went over an hour just by a bit, but I think we did great. So remember, atoms are the basic building blocks of matter and the smallest unit of an element. Atoms consist of a nucleus that contains protons and neutrons, and they orbit that contains electrons around the outside. And then the bonding of atoms creates molecules, and then molecules combined together make compounds. And then the periodic table is an arrangement of all of the elements that we have out there. And a molecule is the smallest part of a pure chemical substance that has all the properties of that one material. So a compound is a substance formed by two or more different elements. So we make we make 10. You guys have heard the word tin can? Well, the old ones were made out of lead and zinc. Lead and zinc together makes tin. Well, they don't make them out of tin anymore because lead's poisonous. We found that out. So we make them out of steel, and then we coat them with zinc, which is galvanization. So when you heard the term galvanized metal, it's basically zinc that's coated on the outside to create to help that product from rusting. So a mixture is a combination of substances held together by physical rather than chemical means. So that's our dirt, our air, right? All those things. And then all atoms of a certain element have the same structure, so they have the same properties. And matter is anything that occupies space that has mass, or something that occupies space that can be felt by one or more of your senses. Remember, we can touch it, we can see it, we can taste it, we can feel it. It's matter. Right? And then the 3 states of matter, solid, liquids, and gases. Memorize that. You'll need that for the rest of your career. And the stability of a material is resulting of the strong bonds between the atoms. Unstable materials have very weak, either ionic or covalent bonding. Thus, they, like our nitroglycerin, right? They are very unstable. And then they do things to make them more stable now that we have more technology. And then this bonding and absorption of heat is known as an endothermic and heat-absorbing reaction. And then the releasing of the bond with the release of heat is known as that exothermic reaction. And then a good example of chemical reactions and their hazards to a firefighter is the toxic materials inside the fire. So, all right, you guys. So the question has come up. How am I getting graded on this lecture? You're not. I just want you to watch it. It's going to be an assignment. So if you choose to click on it and not watch it, that's on you. But I would hope you would spend an hour, read your chapter, spend an hour on lecture, do your quiz questions, and then you're going to refer back to your book and your lectures for your case studies. And I hope you're using all of your Jones and Bartlett products that you have. It's an excellent resource to have. I've been using Jones & Bartlett now for probably 15 years. We use it at the Cosumnes Fire Department. They're using it at different academies across California. It is the book that was accepted by the state of California for Firefighter 1, vehicle extrication, wildland firefighting. So, and I'm not a sales rep for them. I just love their book. They have all their PowerPoints. They all make sense. They're legit, right? So I hope you enjoy it. So expect to see I'm going to go and post this on YouTube right now, make an announcement that it's ready, and then you guys go ahead and watch through that, and then this is going to be our norm, right? So we're going to do a lecture, you're going to have a quiz, and you're going to have a case study, and that's going to be once a week. We have Thanksgiving off. You're going to have a midterm, and that's going to be on Jones and Bartlett, and you're going to have a written final. I've had the question, how many questions are in the midterm? 100. How many questions are in the final? 100. Multiple choice, right? So you get to take a chance. So you got that 25% chance, right? There's going to be 4 answers. My recommendation, these are going to be, all of your quizzes are open book. So there's no reason why you guys shouldn't be getting in the 90s to high 90s in your quizzes, because they're not timed, and you got your book right next to you. Look up the answer. Learn it, right? So I do the same thing for our academy. So if you're looking to go into our fire academy, all the quizzes are actually on the Jones and Bartlett, and they're unlimited time. You only get one shot at it. You can't go back, and once you hit submit on your test, it's done. But if you can go back and you can research those questions, you can spend 8 hours on one of your quizzes if you want and get them all right. So all the information is in that book, the PowerPoints, the lecture notes that you have access to, and then here in our lectures. So, all right, everybody, have a great week, and then we'll see you again next time. Thank you.